we'll go ahead and start looking at the next section. I hope that y'all got to have some good discussions in your rooms, trying to look at those smaller segments. Hopefully the screen sharing between different people in the same breakout room could work. Next thing to take a look at is we don't just look at our data in time and space, especially with kind of complex waveforms. We oftentimes are looking at our data in the frequency domain as well. So now let's look at this section that's on spectral analysis. So when we're looking at this section, if you aren't familiar with the Fourier transform, we've got a little tutorial here to, that you can go through this video and learn about it. But generally, if you're not familiar with looking at spectra of data, just think about at each frequency, how much energy is traveling at that frequency. So let's say if I were to hit like a middle C note on the piano, I would just see one spike in the Fourier domain where there was a lot of energy at that particular little narrow band of frequencies. I might also see some overtones and things like that and harmonics, but generally I'm gonna get like sort of one spike, right? But here, when we're looking at our frequency domain data, and especially from a Vibrasize sweep, we're gonna get a broad range of frequencies. So with the Vibrasize, you might have something like a chirp signature, for instance, where you start at low frequencies and then you work up to high frequencies. If I were to look at just a particular channel and look over the whole window that contained both the low and the high frequencies, I'm gonna get some contribution from all of those frequencies in there. So we've got a function down here to go ahead and plot the amplitude spectrum of every one of our channels within a particular range. So here, I'm just gonna look at one channel. It's gonna be my channel of interest. And I'll look at, I'll pass in the data array, or at least that object. So I've got that function there. And this one is just gonna say for one channel, how much energy is in each frequency band. So for instance, if I look at channel 2300 and run this, I've got a lot of frequency or a lot of energy that's down in this kind of range below 50 hertz, right? If I were to change to say channel, I don't know, 100 and rerun this, it'd be in a different location. It would be a different distance from my source. So there's some attenuation going on there. There's also a difference in what the geometry is there. So this is all gonna add up to a different frequency response. So here you see more of the energy in the low frequency. You also see this kind of like hump coming up at higher frequencies in 100 to 200 hertz. So you can play around with different locations. But just looking at one channel at a time is maybe hard for people to really get a feel for all the data when we have like more than 8,000 sensors. So instead, what we're doing a lot of times is looking at the amplitude spectrum for a lot of different channels at once. So again, we're gonna turn to our friend, the raster plot, and we're gonna have this function down here called plot array spec, where we're gonna plot how much energy is in each of those frequency bands as the amplitude spectrum, not the power spectrum, but amplitude spectrum, from a window that goes from minimum seconds to maximum seconds. So we're just gonna look at a little window of time and a little window in our channels. So we might look at a group of channels that are all close together, or we might look at a lot of different channels. And we might wanna zoom in on just a particular part of the frequency range. For instance, when we were first looking at some of the data from like Richmond Field Station, for instance, we did not zoom in on the very low frequency part. We didn't think there was much there. But if you zoomed in, we could see a little bit more energy down there. And so being able to zoom in on different frequencies of interest is useful for us in our visualizations and exploring these data. We've also got a keyword here. It's going to be a linear color scale by default, but you can also specify a log color scale, or you could even change this code a little bit. And if you want, you can add, I don't know, like quadratic scale or whatever you think would help you to visualize differences between different parts of the array and different parts of the frequency bands better. So let's define that. And you can see there's a bunch of error checking to make sure that you're getting valid time windows, frequency bands, channels, things like that. But where you're really doing stuff is first you calculate your Fourier transform on the channels of interest. Then we're gonna just look at the absolute value of the first half of that. It's gonna spit back basically the spectrum and then a conjugate of that, and we're just going to look at the first half. Then we do a little more error checking on our frequencies, and down here we've actually got our plot. So if you want to modify this code and have different ways to scale your color bar, then you can do that down here in this section. All right, so we've got that defined, and now let's go down here. We're going to choose a particular frequency band of interest. Like, let's say if I wanted to look at 0.5 hertz to 200 hertz, it's pretty broad band for sure. And I might want to look at the whole window, 0 to 25 seconds, and maybe I want to look at my whole array. So I'm going to go beginning channel to end channel. And I'll create my, my plot like this. And in this one, I'm going to use the log 10 spectrum, or the log 10 of the amplitude spectrum to visualize it. So it's going to take a little while to calculate all those Fourier transforms over all of our channels. So we'll just wait for that. So while that's running, one thing I'll point out is that you can also cut down which channels you're working with here if you want it to run faster, and especially as you're starting to look at just little segments of the array, like if you were to look at 2 zigzags within the array right next to each other and just zoom in on those, that may really help you with pinpointing where those corners of the array are, for instance. So that would run faster. I'll be patient and wait a little bit longer. Here we go. All right, so here we've got our color scale. So if you have these numbers here from a log scale, that means log 10 of amplitude spectrum within each of those frequency bands at each one of these channels. So we have not a lot of very low frequency energy, but then we've got this band that's really lines up well with the source spectrum. If you go onto the geothermal data repository for the Brady hot springs by checking out some of the links at the top of the notebook, what you're going to see there is that they also have a source spectrum. So if you're really excited about array processing, you can go ahead and get that source spectrum for the fiber-size source there. I'll add the link into the array processing Slack in a little bit. But if you want to go into it and really do stuff like source decon or cross correlation with the source, you can go ahead and play around with that also and look at how that changes your frequency content there. All right, so for the next close to 10 minutes until 2:10, we're going to be in breakout rooms again. And I want you all to just play around with these tools, get a feel for the spectrum, look over different time windows and look at how does that fiber-size sweep frequency content change over time? How does it change over channels that are kind of closer to the source versus farther from the source? Do you see the effects of attenuation in the near surface, for instance, where your higher frequencies might die off? Or how does the geometry matter in that frequency content that's acquired? Also, just general visualization things, figure out what works for you on using log or linear scale or adjusting and creating your own scale for the color bars. Then for those of you who are more advanced and may want to code up something on your own, think about for a single channel or maybe a collection of channels that you might average their amplitude spectra together. Can you create something to do short-time Fourier transforms and then create like a waterfall plot to see for a particular channel or group of channels, how does that frequency content change over different time windows that are much shorter? So can you see what the spectrum of that source is, or of the fiber size response is as the source is changing? So now we'll go into those breakout rooms again. So feel free to talk about any of these questions or come up with your own questions about the data.